Assalamualaikum and good day everyone. My name is Noshazir binti Amran and today I will be presenting about my chosen topic, which is a metrological control under the ISO 17025 framework. In daily life, we look at nutritional labels or test reports and assume the numbers are absolutely guarantees. However, in professional analytical chemistry, raw data is always subject to small physical variations. So ISO 17025 provides the strict mathematical framework needed to control these variations, converting raw numbers into globally recognized traces. Let us address a basic consumer illusion. So, when a product label reads 500 milligrams, consumer expect exactly 500.0 milligrams. But in the scientific reality of testing, a single perfect number does not exist. Natural micro variations are always present in all testing environments. Analytical instruments are highly sensitive, meaning the exact same sample can yield slightly different results. Science must account for this reality. To see this action, we can look at the example. So, if we measure a single certified 10.00 gram reference weight across 3 different scales, we get 3 distant readings: 10.001 grams, 9.998 grams, and 10.002 grams. All 3 instruments are correct within their limits. ISO 17205 provides the structure needed to manage and report these unavoidable differences. So, where do these changes come from? They originate from a physical chain of events. First, environmental factors like room temperatures, shifts cause equipment drift. Second, the instrument itself has mechanical tolerances. And third, the measurement process introduces subtle handling variations. And the final result is a natural dispersion of data points rather than a single fixed value. Because variation happens, ISO 17025 demands we calculate measurement uncertainty. This is the mathematical range showing the unavoidable doubt in data. Accredited labs can never report a solitary integer. We must report a plus-minus range at a 95% confidence level. This means we are statistically certain the true value falls within this range 95 times out of 100. We map this landscape through 4 quadrants. The first one, environmental shift like temperature and humidity. The second one, calibration status, tracking reference standard degradation. The third one, human handling variations between analysts. And the fourth one, instrument tolerances, defining hardware limitations. Evaluating all 4 dimensions allows us to correctly define our data range. How do we ensure local data matches results worldwide? So we use metrological traceability. This anchors local data directly to international reference standards using an unbroken calibration ladder. To these raw test results comes from lab equipment, which is calibrated against local standards. Those are verified against national standards, which log directly into the core international system of units. However, this anchor relies on a zero tolerance policy. If a single calibration record is missing or expired, the chain instantly breaks. It does not matter how precise the equipment is, but missing documentation completely destroys the legal validity of the laboratory data. ISO 17025 demands a flawless history maintain public trust. To prevent a break, metrological control operates as a continuous life cycle that consists of 4 phases. The phase 1 is the manufacturer sets the baseline specifications. The phase 2 is calibration verifies the instrument against national standards. And the phase 3 is active laboratory testing under ISO 17025 compliance. And the last phase is regular recalibration steps in to prevent natural drift. This loop keeps our data legally defensible. Let's us apply this to consumer safety. Imagine the maximum allowed limit for a chemical is 0.8. A lab tests a sample and gets a raw result of 0.75. On paper, it passes. But remember our measurement uncertainty range. Because of natural variation, the true real-world value could easily be 0.85, crossing into the dangerous territory. This creates a hidden risk. To solve this boundary problem, ISO 17025 uses guard banding. Laboratories intentionally lower their internal acceptance limit by the exact width of the measurement uncertainty. This creates a dedicated safety buffer. If a sample falls into this guard band, it is automatically rejected. This engineered buffer guarantees the actual value never accidentally exceeds the true legal limit. We manage the process using objective decision rules. A clear pass means the result and its uncertainty are entirely within the safe zone, so the compliance is confirmed. Second one, a conditional status means the range overlaps the boundary, presenting too high a risk to approve. And the last one, a definitive fail, means the result exceeds the limit entirely and the product is rejected. Without a guard band, the acceptance threshold matches the legal limit, creating a high risk of falsely accepting an unsafe product. Under ISO 17025 metrological control, the limit is shifted inward. The risk of false acceptance drops to near zero because the mathematical doubt is fully accounted for, making results legally defensible. So, at the end, in conclusion, the value of ISO 17025 goes far beyond a clean laboratory checklist. It is a strict mathematical architecture built to protect public safety. By mastering uncertainty, tracking accuracy globally, and enforcing safety buffers, we convert raw data into absolute trust. By knowing exactly what we don't know, we guarantee safety. So that's all from me. Thank you.